Now that we have seen WALS in action, let's now see what a more productionized version of WALS looks like in this demo. In a later module, we'll be building an end-to-end productionized and automated solution using the larger Google Cloud Platform ecosystem. For this demo, we'll be using the WALS TFT notebook. Let's get started. All right, now we'll be doing collaborative filtering on Google Cloud Analytics data, but this time operationalized. We'll be using TensorFlow Transform to create transform functions that we're going to apply to our data instead of doing it the other way. All right, so this notebook is going to use the WALS matrix refactorization approach to do collaborative filtering. However, we'll be doing TensorFlow Transform to carry out the pre-processing. This way, these steps are automated. We're going to map visitor ID, a string, to a user ID, an enumeration of indices. We're going to map content ID, a string, to item IDs, also an enumeration of indices. We're going to remove already viewed items from the batch prediction output, and we're going to replace the user ID and visitor ID in batch prediction output by visitor ID and content ID. So therefore, we'll now be able to know how they fit back to our problem. First things first, Apache Beam currently only works in Python 2, so we're going to switch to Python 2 kernel in the above menu. You can click the drop down and select Python 2. Okay? Then we're going to make sure that we have the right environment here. Because Apache Beam is only currently for Python 2, we're going to activate our Python 2 environment, uninstall Cloud Data Flow, install a couple other packages like Apache Beam and TensorFlow Transform. Only certain combinations work at the moment, so we're going to choose this one. And after that, we're going to just check to see what the versions we have are, and we're good to go. Before we get started, though, make sure you reset the notebook session kernel so that way all that stuff can be pulled into this session. All right, moving on. As usual, we're going to import your OS and set our project, bucket, and region. And we're going to put those into our environment variables in Bash. Make sure you set your project and your compute region so that this can work. And import TensorFlow since that's what we'll be using. So the first thing we're going to do is going to create our data set for WALS using TF Transform. So for collaborative filtering, we don't need to know anything about either the user or the content. Essentially, all you need to know is user ID, item ID, and the ratings that the particular user gave that particular item. This is our user-item interaction matrix. In this case, we're working with the newspaper articles from courier.at. The company doesn't ask their users to rate the articles. However, we can use the time spent, its session duration, on each page as a proxy for rating. Normally, you would also add a time filter in this, for instance, like the latest 7 days or something, but our data set itself is limited to only a few days, so we don't have to. So just as before, we create our query here to pull all of our data in. Okay, we have our visitor ID, our latest content ID. This is the last piece of content they watched, or read, I mean. The session duration, how long they were on that content, and we're pulling it out of this nested table here. Okay. We then get the full visitor ID, and then we sum up over all the durations, their total session duration ID, and we do a little bit of filtering here. We're going to make sure that the latest content ID is not null because we can't be using null content. And we're going to do a group by full visitor ID and that content ID to get the full duration for that piece of content in case they've seen it multiple times. Also, we want to make sure that session duration is greater than 0 because 0 or less than 0 would make no sense. And we're going to order by the latest content ID so that way we have it in order of use. All right, we can pull that into a data frame here. As you can see here, we have visitor ID, content ID, and the session duration. Okay, visitor ID, really long integer here, and content ID also a fairly long integer. Not going to be very useful for our matrix since they had to be matrix indices, but these are the human readable values. And also session duration here, we're probably going to want to scale that, probably something between 0 and 1. Okay, we want to write out our requirements so that way when we're training locally, we're going to be using the correct package of TensorFlow Transform, version 0.8. And now we're going to create a Apache Beam job in Cloud Data Flow that will use TensorFlow Transform operations that will create a transform function and transform our raw data and metadata into the ones we were looking for. So import our packages as before. We're going to have a pre-processed TFT in this case, rather than without TFT. And it's going to be pulling from a query. And as we know, BigQuery returns a table row, and table rows are basically row dictionaries. where the keys are the names of the columns and the values are whatever they were in those cell elements. Okay, we're going to set the median here that we found by using quantiles. To save us a little time, we just hard-coded it for now. And the result's going to be user ID and item ID and the rating, of course. And here we're scaling the rating so that way it's between 0 and 1 using the median. Okay, here's where we cap it. So any ratings that go above 1 will be capped down to 1 using the great thing about TensorFlow Transform is you can use TensorFlow operations in the Beam code. So we can mix Beam and TensorFlow, get the power of both to get us the best results. So right here, we're just making sure that if anything is greater than 1, we're going to set it to 1 in our rating. And then we return our result. All right, this all gets called by the pre-process function here that takes in my query, and whether I'm in test mode or not, test mode is going to be a local run using direct runner. And in non-test mode, when I want to do the full thing, I'll be using Dataflow runner. So I can have a full cloud Dataflow job kick off. Okay, import some important libraries here. And we're going to have a function to write the count out. Okay, so this will be helping to figure out vocabularies, for instance, vocabulary counts, any other aggregate stuff I can use TensorFlow Transform to do. So to create this pipeline, I first initialize the pipeline here called A, and then I add pieces of pipeline, trying to build this pipe out to feed my data from the initial source to eventually the sink with a bunch of P transforms in between. So you can see here, the first step, I'm mapping my inputs to creating a 1, 1 here. Then I'm combining the counts by key, and then now I'm taking the key values out of that, and I'm mapping it to just the values to return that. And then lastly, I'll write it out to my file here, and with the file name that's provided. Okay. I'm writing TF records out just like we did before, but now I'm using TensorFlow Transform, so I also want to get all these extra assets, like my transform function. So essentially, all this is going to be is a key value list I'm getting with my index columns here. So I'm making a tuple, and I return my key, my indices, and my values. This is my feature map, essentially, of how I'm going to have the data arrayed in my TensorFlow record. I create a job name here, obviously, since I want to be able to track this. Use Stackdriver or any other tools within Google Cloud to see this all. If it's in test mode, I'm going to launch a local job. Whereas if I'm in non-test modes, I want to do the full thing, I'm going to have my output directory not be local. I'm going to have it be on Google Cloud Storage at this path with my bucket that I'm passing in. Okay. So I set some options here and max number of workers so that way I can cap it off. The great thing about Cloud Dataflow is it's elastic, so it can scale to whatever my problem needs. But if you don't want it to scale forever and ever, you can always put a max there, so that way it won't. So as I mentioned, if it's in test mode, we're going to use direct runner, so that way it'll be a local run. Whereas if it's not in test mode, I'll have Dataflow runner to actually create a Cloud Dataflow job that I can then browse and see all the great graph it makes and everything and see what's going on. All right. I do have to set up my metadata schema here since this is TensorFlow Transform. So to do that, I'm going to essentially create column names from my list here, visitor ID and content ID, as I loop through these in creating this dictionary. And my values here are going to be my value schema. They're all strings. Visitor ID and content ID are strings here. Okay, and it's going to be a fixed column representation because there's a fixed number. It's 1 string per column, so I don't have to have any variable length thing. I do want to update my schema here. This is a great way how you can add things to this dictionary, to the schema I'm creating, because session duration is not a string. It's actually a float. So therefore, we can't do it all in one fancy loop. We have to have 2. So we're going to loop through here and create the session duration. Once again, it's 1 session duration per column, so it's going to be a fixed column representation here, as you can see. Lastly, now that it's all done, I have my data schema created. I'm going to call dataset metadata to create my schema. And I'm going to pass it this raw data schema here. That's the raw data. I'm going to use this to create the transform data schema, which will be different slightly. Okay, now that I have that, I can run my Beam job, creating a pipeline, and inside I can pull my query in from above, a couple cells above. And if I'm in test mode, obviously I probably don't want to have, locally on my VM, pull millions and millions of rows in. So I'm going to add a little limit. I'm going to concatenate at the end of that string a limit 100. From there, If test mode or not test mode, I continue on. As you can see, the indentation changes. Raw data, it's going to be my pipeline P that I started with here. And I'm going to add a piece of pipe to it. I'm going to read from my BigQuery source using the query that I have in standard SQL. From there, now I have my raw data. Remember, it's a pipeline, it's a beam pipeline. So I'm going to take the tuple of that with my metadata. Remember, that comes from my schema, and I'm going to put that all together into my raw data set. So it's my data combined with the metadata about that data, okay, like the types and the length of the features, etc. Now is the cool part. Here's where I'm actually going to create my transform data set. So from there, I'm going to take that piece of pipe that I've left off on raw data set, and I'm going to add in a new piece of pipe where I'm going to analyze and transform the data set. And it's going to be using my pre-processed TFT function up above. Now, remember, when we're doing training, we do analyze and transform the data set, whereas in evaluation and prediction, we're going to have transform data set, because we're going to use the metrics and vocabularies that we find from the training data set in the evaluation and prediction. We don't want to recalculate those. Okay, and that will create this tuple of my transform data set and a transform function that I can then take that function and apply it to the other data sets without having to recalculate all that stuff again. All right, so to then take that, I have my transform data and my transform metadata, which comes from my transform data set. Okay, I'm expanding that tuple. Also, now that I have that transform function, I'm going to write it out so that way I can use it in my TensorFlow code, pull the function in. And to do that, I'm going to name it this so I can find it nicely on my graph. And I essentially just call transform function IO, write transform function, and I point to where I want to put it in my output path. Okay, I'm going to name it transform function. Great. Now that I've got that, I'm going to do a group by to create users for item and items for user. Okay, so remember, each item might have multiple users and therefore multiple ratings, and likewise, each user might have multiple items and multiple ratings for those items. So I create a pipeline for each using my transform data. To do this, I take my transform data and I'm going to create a map for items node in my Cloud Data Flow graph, where I'm essentially just taking the item and I'm mapping it to the item ID. Then I group by that on that key, and then I'm going to take these and create my user list and write that to a TF record here of my user list for each item. Likewise, I'll do the same for items for user, except this time, rather than trying to map the item IDs and create a list of those, I'm doing it for user IDs. So for each item ID, we'll get a user list for that item. Lastly, all right, I've transferred my data set. I'm going to have an output schema. What's that going to be in my TF record? I had to have that feature map. Okay, we created something for my input. Now I'm going to do it for my output. So here I'm going to have my key. So my key here is going to be an integer. Okay, it's either my user ID or my item ID, depending on which piece of the pipe I'm in. And it's going to be fixed column representation. I only have one per row. Now, however, the indices and the values, the indices are also going to be int64, and these will be, in case the key is users, it'll be items in this case, and if the key is item, it'll be users in this case. And as you might see, it's going to be a list column representation. Same for values, since these have to be in sync with each other. The reason being, like I said, each user is going to have multiple items that they've interacted with, and likewise for items. And values, of course, are going to be float 32. We've scaled the session duration into floating point integers between 0 and 1, so now we can use this and output that. Now that I've created this, I have to actually write it to the records. So to do that, I'm going to use my users for item section of pipe that I have here, and I'm going to write it to a TF record at the output path with this file name, with this coder here, which is going to be example and protocoder, using the output schema that I defined. Likewise, same was for items for user. All right, I'm also going to write out my count for the users for items, so that way I can get the number of items and the number of users, so I don't have to recalculate those later. Okay, this is basically just the number of items total in all of my data and the number of users. And that's it. I call my pre-process on that query. I'm saying test mode false. I want to do the full data set, please. And it's going to write all my TF records. Of course, you should run the next cell once it's all done to make sure all the records have been written out. And you can check out what's inside your transform function and all the assets it's created. So to summarize what we should have here, you should have a users for item. It's going to contain all the users and their ratings for each item in a TF example format. The items and users here are integers. They're not strings. They were strings, but now we've converted them. Item ID, not content ID, for instance, and user ID rather than a visitor ID. The rating is also scaled. Likewise, we're going to have an items for user, where it's going to contain all the items and ratings for each user now, and it's going to be in a TF example format. The items and users here are integers. They used to be strings, but they're not anymore. So for instance, we converted content ID to item ID and visitor ID to user ID, and the rating has also been scaled. Lastly, from that right count, we have the vocab items and the vocab users, so that way we can have it for both, for the mappings. All right, now that we have that with our transform function written and all of our data processed into TF records, we can now actually train with WALs. This is fairly similar to what it was in the non-operationalized WALs, so I'm not going to go through all of the code here, but we'll just look for the parts that are different now. All right, so we have our protos, we have our decode example as before. All right, everything's as before. We have our remap keys, so that way it can fix some of our what batching does with the indices. And we have my parse TF records here. Okay, and I'm going to read it in my file. I'm going to get the file path, all possible files in case there's shards. Create a data set out of that. I'm going to map my decode example with my vocab size, passing each serialized example. I'm going to repeat a number of epoch times depending on if I'm in training or evaluation mode. I'm going to have a batch of those, a batch of records, and lastly fix my keys and then create it and return. And that gets pulled from my input function here, where I'm parsing my TF records, items for users and users for item, and project rows, so that way I can either have a recommendation model that I'm recommending items for users, or I can have a targeting model where I'm recommending users for items. And that's it. I return features and none because my labels, as we talked about before, they switch. I keep my rows fixed and solve for my columns, and then I keep my columns fixed and solve for my rows. So I'm going vice versa, features and labels between the two. And then lastly, I return my input function since that's what my custom estimator wants. All right, find top K as before. I'm going to try to figure out this using the matrix multiplication. I take the top K items out of there. I'm going to cast those back as integers since they are indices in fact. But we have a little bit of changes here, as you might see. In batch prediction, I'm going to create my lookup. And here, I'm actually pulling in from my assets here, from my transform function that we learned through the beam TensorFlow transform job we made. Okay? This way, I can do a simple mapping to use my vocab of my items and my users to create my original item IDs and the original user IDs. These are the things that are human readable. There's a visitor ID and content ID. So that way I can tie it directly back to my original problem and not the enumerations we created to be able to use WALs. Okay, to do next, I create a session, pull my trained model back in, and I can pull my user factors and my item factors back out using my estimator .get rows factors and get column factors. These should be, respectively, number of users by the number of embedding dimensions we used, and the number of items by the number of embedding items we used. Okay, so we get those matrices back, and then we're going to take this with our top K. We're going to call our function in a map function, so we're going to keep doing this for each user, for instance, since this is going to be a recommendation model here. We're looping through users, and we'll get the user, the top K per each user that we send, okay, in our batch. All right, and then here's where we do our lookups that we pulled in from our transform function. It's a simple mapping because thankfully user ID and item ID are enumerated. They're already indices, so therefore we can just point to that value, that index in the list, and we'll get our originals back. We don't have to do any fancy hash mapping or anything like that. All right, train it as usual. Nothing's really changed since we did it for the normal WALs. Everything's the same. Create our train steps, create our experiment function since this is contrib. Right, create our experiment. Inside of that, we have our WALs matrix factorization estimator. We pass it our number of rows, our columns, the number of embedding dimensions we want to use, where we want to write out the model files, our input function for training, our input function for evaluation, number of train steps we want to do, the number of evaluation steps, and also how often we want to evaluate. Okay, we want to do it often enough that we have good metrics to maybe plot or check, but not too often that we're always in evaluation mode and rarely are training. From there, we call learn runner and run it out and train it up and get our batch prediction. So from there, what we can do is call off our job. We're calling the train and evaluate function above. Make sure that you remove all prior files so that way you don't have any collisions or we don't pick up where we left off. We want to start fresh. Once that's all done, you'll see in your WALS train local folder we made here, you'll see your batch prediction.txt here. And this now will have the correct visitor IDs and content IDs here rather than the enumerations that we would have gotten before without that nice mapping. Our checkpoints, our events file for TensorBoard, our graph, all that stuff. As you can see here, here are our user IDs. They're those large integers again. That's great. That's what we wanted. And K, in this instance, we had it set to 3. So here are the top 3 pieces of content with their content IDs. Notice these are not user ID and item ID anymore. The enumerations, these are back to the raw feature, the raw values that we can now tie back to our problem. Now that you have that done, you can run as a Python module the same code, copy and paste it all into module format into a task.py, model.py, call that off, and then if that all works perfectly, no errors or anything like that, now you can run it on cloud, go for a large number of epochs here, so you go through the data set many, many times, very fast, scale it all out. It's great. This took about 10 minutes for me. Of course, if you increase the number of epochs, it'll take a little longer, but you can get really good trainings then. And to get the row and column factors, you can pull them out by creating a session like we did above, and you can return those matrices, and you can print them, and then you can plot and see how they look in an embedding space. And that's it. I hope you enjoyed using TensorFlow Transform. It's really powerful. It helps operationalize this model and make it much more scalable and do a lot more powerful things with it.